Hi everybody. So question 1 is a question on expected utilities and the impact of utility functions on optimal actions. So in this problem, Davis is trying to get to his meeting, and he has the options of either walking or taking the bus. So if he walks, it will guarantee that he will be only 20 minutes late. And if he takes the bus will come in either 10, 20, or 30 minutes. The amount of time being chosen uniformly at random, but it will take him an additional 5 minutes to get there, the time that it will take for him actually riding the bus. So let's analyze what the expected utility of his both actions for Davis are. So if he chooses to walk, then he will take 20 minutes to get there. And so therefore, his utility function is just -2 to the 20 over 5, which is -16. So that one was easy because there was no randomness involved. But if he wants to take the bus, we have to take into account the variableness of the amount of time that the bus will take to get here. So with 1/3 probability, the bus will take 10 minutes to get here, which means that he will incur a utility of 10 plus 5 minutes to actually ride the bus to get there. It might also come in 20 minutes, and so his expected utility will be 20 plus 5 over 5. And similarly for 30, resulting in a expected utility of -56. And what this tells us is that David should choose to walk, given that he has the choice, because walking will incur for him a less negative expected utility. And we're always trying to maximize utility functions. All right, let's take a look at Pat. So Pat actually doesn't care how late he is. He just cares that he's late. And we can see this because his utility function is just a constant -10 for all positive t's. Okay, and he also prefers to ride the bus because he doesn't like to walk. Go figure. And he will account for that by giving a bonus 5 utility if he takes the bus. Okay, so if he chooses to walk, he will just incur a penalty of -10 because he will be 20 minutes late, and he assigns a constant utility to being late any number of minutes. But if he chooses to take the bus, we'll see that actually in any outcome, no matter how late the bus is, he will still incur the same utility. So if the bus is 10 minutes late, he'll get -10 for being late, plus a 5 utility bonus for just taking the bus. And this will be the true for no matter how late the bus comes, which means that his total utility or expected utility is -5, which means that Pat should actually choose to take the bus because that is the action that will allow him to maximize his expected utility. Okay, and the next question is, can we come up with a utility function that under which, if we try to maximize, we will actually minimize the expected time it will take us to get to the meeting? So the answer to this is actually any negative linear function of the amount of time that it takes for us to get there. And let's take a look at why. So let's choose the simplest linear decreasing function of time, which is just u of t is -t. Okay, under this utility function, the expected utility of any action is just the expectation of the utility of taking that action, where the randomness is the variable amounts of time it will take for the action to get us to the meeting. So actually, I will be explicit and write this as t of a. So t of a being the amount of time it will take for us to get to the meeting. And it will be a function of the action. Okay, and in this case, it will be negative expectation of t of a. right? I've just pulled the negative sign out. And so we can see that if we want to maximize this quantity, we would like to minimize this whole quantity. And what is this whole quantity? This is just the expected time to get to the meeting if we take action A. So we can see this direct correspondence between maximizing this means we want to minimize that. And we also see that like any generic linear function, if we put like some positive coefficient here and some positive offset, or actually positive or negative offset, that wouldn't change that fact because in order to maximize this, we would still want to minimize this quantity. OK, so the next question is a little bit trickier. It's asking us, can we come up with a utility function that will actually make us prefer to be more risk-seeking? Meaning that we would prefer to take an action that will give us an expected arrival time of t, as opposed to an action that will guarantee an exact arrival time of t. So I'll give you the answer, and then we'll talk about why it is. So the answer is any function u of t with a positive second derivative. OK, so for example, let's just choose u of t is negative square root t. OK, so graphically, it would look like this, where this is t and this is u of t. OK, so let's look at two actions. So let's say action 1, you will get to the meeting 2 minutes late, guaranteed. OK, whereas action 2 would take then the probability that you get there right on time is 1/2, and the probability that you get there 4 minutes late is also 1/2. OK, so the expected arrival time is still 2 minutes for action 2, as it is for action A or action 1. But A2 is more risk-seeking because it has a wider probability distribution over these two outcomes of getting there 0 and 4 minutes late. All right, so let's look at the expected utilities of these two actions. So the expected utility of taking action A is just negative square root 2, right? And the expected utility of taking action 2 is just 1/2 times negative square root 0 plus 1/2 negative square root 4, which is just negative 1. And negative 2 square root 2 is approximately negative 1.41. And we can see that in this case, we would actually prefer action 2 because it gives us an expected utility of negative 1, which is less than which is greater than negative 1.4. OK, so why is it that we could choose any utility function that has a positive second derivative? Well, this is easy to explain graphically. So if we look at these 3 points, right, these are 3 relevant points. So 2 will incur a utility of negative square root 2, and 4 will incur a utility of negative 2. Not exactly to scale, but it makes our point. So the point being that if we look at the gaps between the utilities incurred, if we get there 2 minutes late versus 0 minutes late, we can see it's quite large, whereas the gap where we between getting there 2 minutes late and 4 minutes late is quite small. What that means is, given the choice, we shouldn't put all of our probability of being late on 2. And instead, we should spread it out. Because if we spread, say, equal weight on 0 and equal weight on 4, as we did with action 2, then actually putting some probability weight on 0 gives us a much larger gain in utility than the loss in utility that we acquire when we put some probability weight on 4. See, because the gain we get by moving some from 2 to 0 is much larger than the loss we get from moving from 2 to 4, this quantity, it makes sense for us to spread our probability distribution over outcomes t wider. And the reason this is because if the positive second derivative is positive, then our decreasing function, the rate at which it decreases is decreasing. So the gaps between successive times will get smaller and smaller per unit time because the second derivative is positive and the function is decreasing. OK, that's it for problem 2. Problem 2. So let's talk about value of perfect information and decision networks. So let's cover some basics. So in a decision network, we have chance nodes, utility nodes, and action nodes. So decision networks are kind of similar to Markov decision processes that we talked about earlier in the semester, in that you have a sort of state, which you can think of as an assignment to all of your chance nodes. You have actions, and then you have a utility function, which we called a reward function in the MDP setting, which is a function of state and action. So in this case, utility function is a function of a subset of the chance nodes and the action being taken. So, and in this scenario, we want to basically evaluate which is our optimal action to take, just like in the Markov decision process setting. So what is value of perfect information? So heuristically, the value of perfect information is a measure of how valuable a piece of information is. A little bit more specifically, what is the gain in utility that I can expect if I'm acting optimally, if I receive this information versus if I don't? And intuitively, the value of perfect information should always be non-negative, aka greater than or equal to 0, because receiving a piece of information about the world allows us to make a more informed decision. And if we have more information and we always take the action that maximizes our utility given the information that we have, that quantity should only get greater with more information, right? Because we can only make better decisions with more information. So let's look at this specific problem. So in this problem, there is someone trying to buy a car, and the car may be of good quality or it may be of bad quality. If it's of good quality, the car is worth $2,000. If it's not good, it will cost $700 to repair it in order to be in good shape. And buying the car will cost $1,500. There's another part of this decision network, which is that we can do a test on the car to give us an indication of the quality of the car. And this test will not tell us exactly whether the car is in good shape or not. But if the car passes the test, it at least gives us some information that the car is probably of good quality. And conversely, if it fails, it's probably of bad quality. So let's look at what we know. So in the problem, we're given that we have a prior probability over how good or over whether the car is of good shape or not. And this prior probability is indicated here. So it says the buyer's estimate is that C, the car, has a 70% chance of being in good shape. So let's write that down. So this is our prior probability over Q. And the probability that it is of good quality, we give it a 70% chance. And the probability of it being of bad quality, we say, yeah, that's probably about 30%. All right. And in this decision network, these are the chance nodes. This is the utility node, which you can see is a function of this action and the quality of the car. OK? So given no test, let's calculate the expected net gain from buying the car. OK, so what is the expected utility of buying the car? OK, so the first question we ask ourselves is, where's the randomness coming from? So in this setup, the randomness is coming from the quality of the car, because that's what we're unsure about. What we do know is that we have this prior probability over what we think the quality of the car is. So with 70% chance, the quality of the car is good. So if the quality of the car is good, then the utility we gain by buying the car is $2,000 minus the amount we paid, which is $1,500. And if the car is bad, then we get a utility of $2,000 minus $700 that we did for the repairs minus $1,500 that we bought the car for. And in total, this comes out to 290. So our expected utility of buying the car is 290. I'll note that the expected utility of not buying the car is just 0. And I'll actually write that here. I'll just write not buy is 0, right? Because we expend 0 money to buy the car, but then we also get 0 money in return because we didn't do anything. So in this scenario, we should actually choose to buy the car. If we weren't given any other information, this was all we knew, this was our prior probability over the quality of the car, we should just choose to buy it because buying it will give us an expected utility of 290. So now the scenario gets more interesting. We can perform a test. If the car is of good quality, it is likely to pass the test. If the car is of bad quality, it is unlikely to pass the test. Okay? So from this, we would like to know what is the probability period of a car passing the test, and what is the probability that it's of good quality if the car passes the test, and what is the probability that it's of good quality if it doesn't pass the test. Because what this gives us is probability of t given q, but really what we're interested in is what is the probability of q given t, right? Because we can perform the test, and once we know the result of the test, we want to know, okay, how can we update our belief over what the quality of the car is. So let's do the first part. So what is the unconditional probability that the car passes the test? I'll partition this probability using the law of total probability over the qualities of the car. So I'll just shorten this to pass, and we're going to partition over q equals q. Okay? And q could either be plus q or negative q. Excuse the notation. But this just comes out to, I'll write out the sum. It will just be probability passing and plus q plus probability passing and negative q, right? And this we'll just use product rule because what we know is the prior probability of passing times the probability of passing conditioned on the quality being good, and same for the other half. We know the prior probability of it not being a good car, and the probability of it passing if it isn't. Right? And then these are all quantities that we know. So I'll just plug in the numbers. This is just 0.7. This is 0.9. And this is 0.3. And this is 0.2. Added together is approximately 0.69. Great. So now we want to know what we're really interested in is what is the probability of q given t. So, okay. So the probability that a car is of good quality, given that the test passes, is, I'm going to use Bayes' rule here, is this joint divided by the probability of passing. And luckily, we computed this joint earlier, which is just 0.7 times 0.9 divided by the probability of passing, which we also just computed, 0.69. And this is approximately 0.91. Conversely, what is the probability of it being a good car if the test fails? Well, let's also use Bayes' rule. Divided by the probability of failing. And we actually know these quantities too, because we can just break this up as probability of it being a good car, our prior probability, times the probability of the test failing if it's a good car. So it will be 0.7 times 1 minus 0.9, which is 0.1, divided by the probability of failing, which is just 1 minus the probability of passing, which would be 1 minus 0.69. And this comes out to approximately 0.22. All right, so let's look at part C. So now that we've computed these probabilities, let's use them to figure out what the optimal decisions are. So let's look at the expected utility of buying a car if we happen to pass the test. OK, so again, where's the randomness coming from? The randomness is coming from the fact that we still don't know what the probability of the, well, we still don't know exactly what the quality of the car is, but we do have some information indicating that it's probably a good car because it passed the test. All right, so we can break this up as the probability that the car will pass the test, conditioned on the fact, the probability that the car is good, given that it passed the test, times the utility that we'll get if it's a good car, which we've already computed before was 500, plus the probability that it's a bad car, given that it passed the test, times the utility that we would incur if it was a bad car, which we already computed was 2,000 minus 700 minus 1,500, which is negative 200. So plugging in these numbers, we said this was 0.91. And we said, and this was just 1 minus that. And so this is a positive value, and this is 437. All right, so now let's look at what happens if we fail the test. So similarly, the randomness is coming from the quality of the car, conditioned on the fact that we failed the test. All right, so similarly, all right, if it's a good car, we get a utility of 500. The only thing that's changed in this scenario is what we condition on, which will change the probabilities of the car being good or not. And this, we evaluate, we just plug in what we computed before, which is 0.22, and this being 1 minus that. And this is actually a negative quantity, because this is negative 46. OK, so let's analyze this. So if we do the test and it happens to pass, we should buy the car, right? Because we will get an expected utility of 437 versus the expected utility of not buying the car, which is 0. If we fail the test, however, we should actually not buy the car, because we will incur a utility of negative 46, whereas by not buying the car, we will just have a utility of 0. So it's actually better for us to not buy the car and just break even than it is to buy the car if we fail the test. OK, so now let's analyze what was the value of doing the test. What did we gain? So we defined the value of perfect information as the difference between, and the value of perfect information of as a function of some piece of information. So in this, I will write this explicitly as actually just capital T, because capital T is our random variable, and we're asking what is the value of perfect information of knowing the outcome of this random variable, right? So this random variable indicates what is the outcome of the test. Did it pass or did it fail? OK, so the value of perfect information we define as the maximum expected utility of that we can get if we perform on the test. So for maximum expected utility, what's inside is some evidence minus what we knew before. And in this case, we had no prior evidence, so we're just going to write this phi to indicate an empty set or no evidence, no prior evidence. All right, so let's compute this value first. So this has some randomness in this quantity. And the randomness comes from basically what is the outcome of the test. So this is actually an expectation with respect to the outcome of the test. So we'll write this as the sum of the outcome of the test. And I'll write small t for the outcome of the test times the maximum expected utility of knowing the outcome of the test. Okay, so note the difference between this MEU of capital T, which has some randomness in whether the test passes or not, versus this MEU of lowercase t, in which case there's no randomness in the outcome of the test because we know what the outcome of the test is. Okay, and so let's just write out the numbers. So there's two options, right? The test could either pass or it could fail. So what is the probability that it passes times the maximum expected utility we could gain if it passed, plus the probability that it fails times the maximum expected utility we could get if it fails. OK, let me just correct that. So we computed these quantities. So right, we computed this as 0.69 times, OK, what is the maximum expected utility we could get if we knew that the test passed? So we already know that our two options, right, for actions and their respective utilities are we could buy it and get 437, or we could not buy it and get a expected utility of 0. So in this case, the maximum expected utility that we could get is 437, right? We could maximize our expected utility by choosing to buy the car if the test passes. And the probability that the test fails is just 1 minus 0.69. And the maximum expected utility we could incur if the test fails is actually 0, right? Because our two actions are buying or not buying. If we choose to buy, we actually get a negative expected utility. So we don't want to do that. Because we will next compute this quantity. OK, so what is the maximum expected utility had we not known anything before? And we actually already know this because in the beginning, we only just assumed we had this prior probability over the quality of the car. And we said that if we bought the car, we could expect a utility of 290. And if we didn't buy the car, we could expect a utility of 0. So the maximum expected utility, given that we didn't know anything before about the test, was just 290. So I'm going to write 290. So really, the VPI is this thing minus 290. OK, so I'll just put a minus 290 on all of these. And this comes out to 11.53, approximately. OK, so what does this mean? Well, so the question said, what if it took us $50 just to perform the test? Should you perform the test or not? And the result that we've computed actually says that no, we should not do the test, because the expected gain in utility of doing the test is 11.53, which is not worth the $50 to perform the test. So actually, in this case, what we should do is just choose not to do the test and just choose to buy the car unconditionally. Yeah, all right, that's it for question 2. All right, let's talk about classification. So our problem setup is that we will have some data described by some array of features. So I'll call those features x1 through xn. And we want to take these features and we want to assign a label to that piece of data. Meaning, or in other words, what class of our predefined classes does this data belong to? So let's give a concrete example. For example, spam classification. Our data would be an email, and we want to figure out, is this email spam or is it not? And there are various ways we could represent an email in a way that we could deal with. One is a bag of words model that we talked about in lecture, which is, let me represent the email as a dictionary mapping words that appear in the email to the number of times that they appear in the email. So you might imagine that if the word prince if the word prince shows up a lot, the email might be spam. Or if the email prince and the words prince and donation show up in the same email, probably even more likely to be spam. So our goal ultimately is to figure out what is the probability of the data belonging to a certain class given the features. All right, so this is always our goal to figure out when we're doing classification. So let's talk about naive Bayes. So this might be very hard to do maximum likelihood estimation on. In naive Bayes, we make a simplifying assumption, though, that actually makes computing this probability, P of y given the features, quite easy. So what is that assumption? So in naive Bayes, we assume that the data has a structure or can be modeled in a very specific type of Bayesnet. And that looks like this, where we have the label, what each feature might be. All right, so our Bayesnet looks a little something like this. All right, and it will have a bunch of arrows going to all the xi's. So what's nice about this is that if I condition on the label, then all of the features are conditionally independent, right? So I can write that xi is conditionally independent from xj, given that I know what the label is, right? So why is this useful? Well, because now if I use Bayes' rule on the probability that we're interested in, I can break it up like this, right? I'll write the joint with all the data divided by the probability or the likelihood of the data. And this thing, I can now do my Bayesnet factorization, but it factors really nicely because I can write it as P of y, P of x1 given y. And now I can write P of x2 given x1 and y, but because x1 and x2 are conditionally independent given y, I can just write given y. And you can see I can just write all of the P of xi's. I don't have to condition on the other xi's because they're all conditionally independent given y. So I can just write it like this, divided by P of x1 to xn. Right? So basically, I can write it as P of y times the product of all of the P of xi's given y divided by the probability of all of the features. So why is this nice? Well, we've just simplified figuring out what this huge joint probability is, right? So even if we had all the CPTs in our Bayesnet, we've just made computing this computationally much more efficient. Let's do an example. In this problem, we will assume that all of our variables are binary, which in the example of spam classification might mean y might be spam or not, 1 or 0. And A and B might be 2 words, say like print and donation. And it will be 1 if the word print appears at all in an email, and it will B will be 1 if the word donation appears at all in the email. All right, so 3 nodes, binary Bayesnet. OK, so if we model each of the random variables as a Bernoulli random variable with some parameter that dictates how likely that variable is to be 1, we can derive the maximum likelihood estimates for that parameter. I will omit the derivations because they are in the notes, but just know that the maximum likelihood estimates for each of these probabilities is just what you would imagine it to be, which is just the count of the number of data points that correspond to the data marginalized so that the probability table adds up to 1. All right, so what does that look like? It's very easy. So our estimate of what probability of y is will just be the number of data points in which y is 0 divided by the total number of data points. Right, so here we have 10 data total. Each of these columns is a different data point. And we see that in 6 of them, y is 0. OK, so our maximum likelihood estimate of the probability of y being 0 is just going to be 0.6. And similarly, the maximum likelihood estimate of our probability of y being 1 is just 0.4. And so if we were modeling y as a Bernoulli random variable, its parameter would be equal to 0.4. So similarly, we know that these 2 slots have to add up to 1. So what we're going to do is we're going to count the number of emails. We're going to look at the emails in which y is 0. All right, so the not spam emails. And we're gonna look at the emails in which A was 1 and A was 0 in these two subsets of emails. All right, so here we see that A was only 0 in one of the emails. So we're going to say that our estimate of this probability is 1 over 6, divided by 6 because that's the number of emails in which y was 0. Similarly, these two have to add up to 1, so this is going to be 5, 6. So 5 out of 6 of these emails have A equals 1 and y equals 0. And similarly for here, this is going to be 3/4. This is going to be 1/4. And looking at these, we are going to have 4/6, 2/6. And here we are going to have 3/4 and 1/4. So that part's pretty easy. So what's more interesting is let's figure out, given the data, how we should label a new incoming data point. Okay, so our goal here is to find basically which is larger. Is it the probability y is 0 given A equals 1, B equals 1? Or the probability that y is 1, given A is 1 and B is 1. OK, so now going back to our naive Bayes assumption, we said that we could write this probability in this form. And note that if we are just comparing these two probabilities, we can ignore this denominator, because the denominator is the same for both of these probabilities. It will just be what is the probability of A is 1 and B is 1. And we actually don't need to know that in order to figure out which of these is larger. OK, so actually what we need to be comparing is just the numerator. So in this case, for this probability, the numerator is probability that y is 0 times probability that A is 1, given that y is 0, times probability that B is 1, given y is 0. OK, and luckily, all these values we know because we can just look at our maximum likelihood estimates from the data. So we know that we estimated that this is 0.6. We estimated that this is 5/6. And we estimated that this is 4/6. All right. And what is the and this, let's calculate the numerator. So, so for part 2, the numerator is probability that y is 1 times the probability of the data given that y is 1. So in this case, this would be 0.4 times 3/4 times 3/4. And under this scenario, we find that this value is larger. So we are going to choose to classify our new email, say, as not spam. OK, we're going to choose, we're going to say the more likely label given data. Our data is y equals 0. OK? Now let's talk about Laplace smoothing. So let's first motivate it. So let's say that in our data, say we were very unlucky. Let's say that spam is quite rare, and that we happen to get data in which we only had y was 0. OK, so our data kind of looked like if this was our data, right? Say we had like 10 pieces of data. It was just like zeros all the way through. And then the A's and B's, you know, could have been anything. I don't know. Not too important. But say we had like 10 emails, and y was 0 all the way through, right? We got 10 emails, and they all happened to be not spam. What does that mean for our what does that mean for our maximum likelihood estimates of the probabilities? Well, that means our maximum likelihood estimate for P of y is just going to be 1, right, if y is 0, and 0 if y is 1, right, just by counting. Now the problem with this is now if I want to classify this new incoming data point, say this new income data point is A is 1, B is 1, right? Our email mentions both prints and donation, right? We would probably want to classify this as 1, but if we do our naive Bayes and we just look at our probabilities, our probability for our likelihood for y being 1 is just going to have a 0, right? This is going to be 0, while this is going to be 1. So actually, since this is 0, it actually doesn't matter what these are. We're just going to classify all future emails as y equals 0, right? Because this is 0, all future emails, we're just going to assign a label of y equals 0. And that doesn't seem quite right, because it might just be that we just happen to get bad training data, and we shouldn't adhere too much to our data. This is what's colloquially known as overfitting, and Laplace smoothing is a technique used to combat that. So what is it? Basically what it is our current maximum likelihood estimate of P of y is number of emails, and I'll actually use an explicit value of y, is number of emails with y equals y divided by total number of emails. All right? And what we are going to do with the Laplace smoothing is we're actually going to give each bin some prior counts. And then we're going to have to normalize it so that everything still adds up to 1. What does that mean? Say we do a Laplace smoothing with k equals 2 in our case. Basically what we're going to do is we're going to add 2 to the numerator of everything, and we're going to add 4 on the bottom, just so that the probability is all summed to 1. All right, so here in our case, in our example where we got 10 emails where they were all not spam, instead of this being 1 and 0, right, 10 over 10 versus 0 over 10, we're actually going to write 10 plus 2 divided by 14. And here we're going to write 0 plus 2 divided by 14. So you see how we gave the category of y equals 1 an extra count of 2 just to begin with. All right, so now it turns out that this probability is going to be non-zero, and this is going to be close to 1, but not exactly 1. This is nice because now when we look at our likelihoods, it may not be that since this will not be exactly 0, it is still possible for us to classify a new email as y equals 1, even though we didn't see any y equals 1 emails in our original data set. Basically, Laplace smoothing corresponds to us having a stronger uniform prior on our probability tables. And we can see this because if we let k go to infinity, then our estimates for P of y will all approach some constant value, right, 1/2. All right, so let's fill out this table then with a Laplace smoothing factor of 2. So basically, all we have to do is add 2 to the numerators of all these probabilities and just divide by whatever will make what's supposed to add up to 1 still add up to 1. So this we're just going to say it's 3, and then because we still need these two squares to add up to 1, we're going to divide by 10. This is going to be 7 over 10, right? 5 plus 2. And this is going to be 3 out of 6 instead of 4, and it's going to be 5 out of 6. All right, and that's Laplace smoothing. And that's it for the worksheet.